Hello guys, this video will be composed of bunch of random stuff I'm doing, like trying to learn AI, trying to code, reading papers, trying to understand like CUDA, Triton, everything. And sometimes it will be interrupted. It's just short clips I recorded from everything. You can check the timestamps, the chapters, to read which part of the video teaches what. I'm showing you my channel here. This is not related to the video. I'm just showing you my channel. If you want to watch any of these videos, go to my channel. Moonshot AI released Kimi Researcher. End-to-end, so this is just deep research. Explores over 200 URLs per task. So it's built on top of this Kimi K1.5. Where are these models coming from? I think I saw this already. Better than 01. It's actually good. No, I think it's good that they compare it to 01 and not 03, because they are open source company and they shouldn't compare this to the best model in the world. They're not even meant to be the best in the world. So we got Kimi K1 and Minimax M1, both reasoning models. Maybe I'll check their papers. So back to the deep research, it achieves 26.9% on humanities last exam. So I think now this humanities last exam, if we get like 90 to 100%, are we actually gonna get top level researchers or scientists? Probably yes, because these are probably the easiest questions. So if it gets to like 90 to 100%, then it's also able to solve like really the most difficult questions that human scientists are currently solving. So we get like super scientist AI then. And 4 attempts of 40%, which doesn't really make actually it does make sense. So you give it 4 attempts and it gets 40%. It's good because we can just if it's working on tasks that we don't know the solution to, we can just check each of the 4 and we can find a good solution, because we can just logically check and find mistakes in other solutions, but then we can see one solution and see that it's correct solution, so maybe this will solve some scientific problem. But then why is it not solving scientific problems, or is it? I'm not sure. Guess 40% sounds really high. So it should be solving some novel scientific problems now. It goes from 8.6 to 26.9 after end-to-end reinforcement learning. I don't know if this is base model or the reinforcement learning model, but this model also has data on the internet, so that's why it can find more information and solve more problems. Providing compelling evidence that end-to-end agentic reinforcement learning can significantly advance agent intelligence. I agree. In my last video, new paper perfectly shows how and when LLMs reason and don't. This new paper, Omega, actually it does show that LLMs reason in a more specific narrow way, but even that narrow way is enough for these type of tasks that are not so difficult, just summarize text. So it becomes so useful then. And you can say it's more intelligent. I guess it is, because if we see what artificial intelligence means, it is more intelligent. Then on this new benchmark, XBench, that's made to test real-world usefulness, as it says here, they achieved 69% pass at once, so first try. Average on 4 runs means that they test 4 times, and the average of those is gonna be 69. So I think it's good to average like that. Outperforming models such as O3 with search tools. I guess this is not deep research, this is just O3 with search tools. Actually, I see now, so they have O3 just with search outperforming these deep research guys. So I think then they are comparing it to this, and I guess this is 65%, and Kimi Researcher got 69%, so I think it's best here then. Here you can see humanities last exam. Kimi Researcher gets more than Gemini Deep Research, OpenAI Deep Research, so it gets most. And in XBench Deep Search, Yeah, it's 65. It's evaluated on text-only subset without tools. I don't know what that means really. I guess for humanity's last exam maybe. So here we can see that it's improving the pass rate as the training goes on. So more steps, higher pass rate. Actually, this blog also shows all of the infrastructure. It's actually quite a nice blog showing everything. Okay. Earth's largest decentralized synthetic data generation run. I remember synthetic data not being good, but for model training causing collapse. But I also remember they figured out, other companies figured out some tricks, so it's not so bad anymore. And I would imagine that, synthetic data generated by model would be better than just Reddit random posts, random comments, but needs to be somehow processed or filtered, because there are probably some bad things about it. But I will learn more about synthetic data and make some videos about it as well. I guess synthetic data would be like we generate a bunch of data and then we somehow design some methods to select the good data. So humans would kinda decide what's good data, what's bad data, which AI cannot decide, and then we would train the AI on just that good data. And then we are kinda still distilling human skills into AI then. So the value there comes from humans deciding which data is good. That's why we can train better AI. For me, it's a way to even more and stronger unify the image and text pre-training. That's just my idea. I don't think anybody did that. So that way the images and text knowledge gets more interconnected, as opposed to right now where they just Frankenstein stick together different like encoders for text and video. But one of the problems with these large language diffusion models is long context window. There is no too much research on that at all. However, unlike autoregressive models, for example Llama 3, that gets a lot of high perplexity and high confusion if you try to give it longer context window than it was trained on. Seems like these diffusion models can handle it a lot better. So it seems like these diffusion models can have their context window extended a lot easier. So this new research from Fudan University and Shanghai Innovative Institute and Shanghai AI Lab aims to learn more about extending the context window of diffusion LLMs. LongLad, and LADA is this adaptation of Llama architecture to a diffusion LLM, unlocking long context capabilities in diffusion LLMs. So this LongLad is a method of extending the context window without fine-tuning or continued training. Here we can see what happens if we have Llama 3 autoregressive base and instruct. So if it trains on 8K tokens, 8K something, and you just try to inference it with more than 8K, perplexity skyrockets, which means probabilities of the token generation get high, random, it doesn't know what to generate next. While LADA, the diffusion model, works surprisingly well and perplexity stays okay, even if it's trained just on 8K tokens. We see here some benchmark, and if we look at blue and green, 8K tokens accuracy drops dramatically after, keeps dropping until 16K and then goes to, I guess, near 0 or 0, while the diffusion model, actually accuracy starts dropping at 4K. Maybe diffusion models are not as good as autoregressive models, so that's one problem. But there is no steep drop off at the training window context length. So it means they are less vulnerable to context length extension. So there are some issues here. You see that it does start falling off even if it's trained in this context length. So it seems like these diffusion language models can only attend to maybe specific part of the context more than others or something like that. So we will try to figure out together with this paper the issue. So it looks like diffusion model can see only the local part, maybe around or the context that they are currently processing. So this behavior is described as local perception or sliding window effect. They can handle long inputs, but only pay attention to the end of it. We will understand further. It's confusing for me a little bit as well. Authors theorize that this difference is due to how the models are trained. Diffusion models use bidirectional attention. They can look both forward and backward in the text. Yeah. This means during training, LADA learned about both positive and negative relative positions. Example, the relationship between word 500 and word 1000, and also between word 1000 in reference to word 500. You know how diffusion LLMs, they have some block of text and they don't try to predict the next word, they try to predict within that block some words in some what can be random order or not so random, but seemingly random order. So they start with the whole block of words masked, for example 100 words or more, and then they try to unmask or predict some of those words one by one until the end where they have all of the words unmasked or predicted. Autoregressive models only see past context, they don't see future context, future tokens. So authors theorize that this somehow makes diffusion models inherently more robust because maybe they are trained in more general way where they see both future and past tokens. So the researchers here just apply this NTK based rope extrapolation, which allows the model to attend to 6 times increased context size, context window without any retraining. They call this method LongLad. So it's not a new model, it's a new method. So they say that this is the first time there is some research that shows how to extend context window of diffusion LLMs. If you ask Gemini 2.5 Pro, teach me about life, it's actually good advice. You are not your thoughts. You get random thoughts throughout the day. And they might not be true. They might be random, negative, whatever. You are the sky, not the clouds that are passing. That's crazy. I can show you what it did here. I just said, teach me about life. This paper, Language Modeling by Language Models by Alan AI. It's using language models to generate new architectures for AI and discover good ones. And it discovered good ones. GeoGate, core idea, a novel variant of the transformer. It replaces the standard multi-head attention mechanism with a new called geometric gated multi-head attention. This new attention mechanism is designed to better handle positional information and reduce bias found in standard attention. HippoVQ, a recurrent architecture that draws inspiration from models designed for continuous signals like Hippo. It uses an event-driven mechanism to decide what information is important to keep in its hierarchical polynomial memory, okay, which is also compressed using vector quantization. And then streaming ResNet MLP, an evolution of ResNet architecture. It introduces multi-scale retention mechanism, allowing it to efficiently process data in streaming fashion for real-time application. This design aims to strike a balance between high performance, memory efficiency, and low latency for inference. So they use these LLMs, GPT-4o, Claude 3.5 Sonnet, OpenAI O1 Preview, and O1 Mini. I think if they used the Gemini 2.5 Pro, it would be a lot better. It's a lot better than all of these models. Maybe Claude 3.5 Sonnet is also good. They have this proposer agent that's gonna read some papers and propose architecture and modification. Let's combine the state space of the core Mamba with the feed-forward network of a transformer. They actually have a bunch of these agents: reviewer, planner, coder, observer, etc. So they designed 1,000 and something unique model architectures, and 1,062 of those were successfully pre-trained and evaluated. The experiments spanned a range of model sizes from 14 million to 350 million parameters. 14 million, that's crazy. So that also like works. 2.7 million lines of code. So they ran thousands of cheap experiments with 14 million scale and only promoted the most promising candidates to the more expensive 125 and 350 million scale. They also compared just telling the LLM to generate whole code versus creating these agents. And agents work 92% of the time, and just direct prompting on one LLM, just 6% of the time, it successfully created fully working, coded, fully working model. So for complex multi-component code generation, it's good to break problem down into agents and verify each piece individually. More effective than trying to generate it all at once. Here they compared some of the architectures. So GPT, Mamba, so these are human design, and these are theirs. So this is GPT-2, and they are competitive, but these are older generations. So I'm not sure which architecture they use. Maybe this could be improved. I think it's good. The results are good. I'm still thinking, how can I, as a single person without like too much GPUs, maybe improve these AI models, like running this generational architecture or whatever. So I feel like I just need to learn, because there is no way for me to train these big models, and even a small one takes a lot of time. Maybe if I somehow put like 8 H100s or something, so I can train it quickly. But on free Google GPU, which I don't even have money right now for H100s, but maybe in future, like in the next few months or half a year, I can look for some research grants or some financing for research. New Gemini CLI has 1,000 free Gemini 2.5 Pro requests per day. What? It looks really nice here. You can just install it and start talking to it. Like here, write me a Gemini Discord bot that, yeah. Matrix multiplications are key building blocks of most modern high-performing computing systems. They are notoriously hard to optimize, hence their implementation is generally done by hardware vendors themselves as part of so-called kernel libraries, for example cuBLAS. Unfortunately, these libraries are often proprietary and cannot be easily customized to accommodate the needs of modern deep learning workloads, for example fused activation functions. So this is matrix multiplication Triton tutorial in Triton documentation. So in this tutorial you will learn how to implement efficient matrix multiplications by yourself with Triton in a way that is easy to customize and extend. Roughly speaking, the kernel that we will write will implement the following blocked algorithm to multiply mk by kn matrix. If you just go to my channel and search for Triton here, so there is 4 of them here. This matrix multiply shows basics as well of matrices. Maybe you should watch this one first, Triton code from scratch, if you don't know anything. So this is the implementation in Python of what we will do, but later in Triton. So we have we go from 0 to m, which is number of rows, but we only take some number of rows, not entire all of the rows. And then same for columns, we go from 0 to number of columns, but we just take some number of columns. So these two will just mean like if we have some matrix, we will just take some maybe number of rows and number of columns, so this smaller tile of matrix. And then we'll take same, so in the next iteration we will take some other columns. So we go left to right and then different rows and then different rows below, etc. So that's how we go. and the accumulator will be just zeros in the beginning of block size m, block size n. So this is the tile that we are calculating, so block size, not entire. Okay, and then for k we will also do now k. So we will have two matrices. I was showing you an example on one matrix, but actually the first matrix we will have rows times k columns, and then second matrix we will have k rows times n columns, and then we will multiply those two. So for k, and k is the same dimension, we will go first take from A, we will take these rows, so from first row that we are starting with to the block size after, and then take same for k columns, and then here for B same, and then we will accumulate by taking the dot product. Now this is gonna be accumulating a few times to the same numbers. If this is confusing, I explained this in the Triton examples video, or you can also take this documentation and ask ChatGPT why, because I understand this, so I will not. It's not good for me to do this all the time, the same thing. So you can just ask ChatGPT to explain how this accumulate works, and then later in C, this is our result. We will just save the numbers at the positions from this m to m block size and n block size. But basically, you know that in this dot product, or actually this is matrix multiply. In matrix multiply, you need to multiply these every two pairs of numbers of elements and then add them all together. So the thing is, you don't need to multiply all of them and then add them all at once. Actually, you don't need to do that. Instead, you can just multiply some part of it and then add, and then multiply next few numbers and add, and then next. So that's what we are doing. So here we are not multiplying entire k or entire rows. We are just multiplying part of the rows, part of the columns, and then add them, and then multiply next part, and then add next part, and add. In the end, after all of this, we will have multiplied entire block size m and block size n, where each iteration is doubly nested for loop is performed by a dedicated Triton program instance. Then m to m plus block size. So let's say we are processing row number 2 and row number 3 with those indices. So we just get 2 to 3. And so that, because we have 2 and 3 rows, but we need to, because the matrix in memory is flattened big array, we need to find actually where those rows start, which index they have in the matrix, which matrix in memory, because in memory is just one big array. So first we broadcast 2 and 3 to have shape from 2, so shape 2, we broadcast that to 1. So now both 2 and 3 are in separate brackets, so we have one bracket outside and then inside 2 elements, and each element in its own brackets 2 and 3. So this is broadcasting, so this is keep this dimension, which is 2, and then add 1 here. That's how you broadcast. This is because we want to have this as arrays, separate arrays. So, and then stride for A is the length of the row, because in memory, row major layout, it's stored first row, then second row, then third row, but all in a single one vector, 1D vector. So if we want to start second row, we need to calculate how many elements in that single vector to move forward. So if one row is 4 elements, and we need to see row number 2, so zeroth row is 0, 1, 2, 3 elements. Row with index 1 is 4, 5, 6, 7. So row with index 2 is 8, 9, 12, 11 elements. So this will actually just multiply by stride of 4, those 2 and 3. So you will get 8 and 12. So now we have 8 and 12. Here, just 8 and 12. And here we have, let's say, whatever, 0 to 4. And we broadcast to 1, 2. So it's different. Now it's 1, 2. So now we just have also 0 to 4 in brackets. Not separate brackets, 1 brackets, 4 elements. But 1 brackets around as well. Because it's 1, 2. 1, 4, sorry. Dimension is 1, 2. Number of elements is 1, 4. Wait, what am I doing? Yeah, it's 1, 4. Dimension is, so if this has dimension 4, this will have 1, 4. And stride for columns is 1. So we will multiply the same thing by 1, so we will get 0 to 3 anyways. 0 to 3 is indices, so we will get some array 0 to 3. And then we will multiply, so 8, 12 times 0 to 3, but this is, this is in rows. And this is in columns, so you see how it's broadcasted differently. So when we multiply them, we will just get 8 times 0 to 3 and 12 times 0 to 3. They will be separately multiplied. So we will get, in the end, 8, 9, 10, 11, and then 12, 13, 14, 15. Those are indices in the memory for this matrix, these elements, current elements, and same for B. We do same for B, and that's it. I just told the Gemini to create Triton tutorial in this new Google Colab notebook, and it already created a plan. And now it's executing step by step, and it's been creating all of this good stuff. I don't know why it did this here, but I guess it runs. And then it described everything here, and it's creating new stuff. I don't know why it's doing it in this code block. I think it's getting a bit confused. Maybe they're gonna fix this soon. Actually, it just works still. It just writes this, I guess. Okay, accept and run. Create a simple model. Okay, let me accept and run. So am I at, yeah, I'm CPU. I guess, okay, no module, doesn't matter. Let's see. Yeah, it says here to install this first. Accept and run everything. Create simple model is still going. Okay, I'm just like accepting and running everything. This is so interesting. Okay, so you get the point. You can just keep creating this stuff. I think it's really good, really interesting. So here we have about 7 iterations or steps per second. That's float 32. So if I change it to float 16, then if I just run the same training again, let's see the speed up. We'll wait a bit. Oh my god! It's 24 iterations per second. Wow, this is so fast. We got an error. So there is this TileLang where it's similar to Triton, where it's made to streamline the development of high performance GPUs, CPU, accelerators, kernels. It has 1.3k stars. So if I scroll down, we can see flashy logos. It reminds me a lot of Triton. So I want to see what's the deal with it. Should I learn this instead of Triton? It has all of this good stuff, matrix multiplication, flash attention, etc. There is also this multi-head latent attention. That's crazy. This is DeepSeek's multi-head latent attention. DeepSeek actually open sourced it as well. I was not aware that this was the repository for the multi-head latent attention. Actually, I was trying to implement it myself as well. This MLA could be answer to reproducing or creating smaller LLMs that are near huge LLM performance. So here the benchmark shows T-flops, that is compute, versus KV context length. I guess they wanna show that flash attention and TileLang are the best, and then Torch and Triton. Triton is not so good, but I don't get it because it says like it's using most compute for the KV context length, so I guess you wanna use less compute. I'm not sure. I don't get this chart, I don't get this benchmark. But we can see that TileLang is performing similarly to flash attention, although I don't know why Triton is supposedly so low. Maybe it's not well implemented, I'm not sure. TileLanguage is a concise domain-specific language designed to streamline the development of high-performance GPU, CPU kernels, like GEM, DQuant, GEM, flash attention, linear attention, by employing a Pythonic syntax with an underlying compiler infrastructure on top of TVM. TileLanguage allows developers to focus on productivity without sacrificing the low-level optimizations necessary for state-of-the-art performance. We see installation, guides, tutorials, deep learning operators. Let's check general matrix multiplication. Let's see. There are 3 levels. One is without knowledge of GPU architecture like cache tiling. Level 2 is being aware of memory tiling thread blocks, but user not willing to drop to the lowest like thread control. And level 3, a user takes full control of thread level primitives, etc. The code is almost as explicit as handwritten CUDA or HIP kernel. I don't know what HIP is. This is some code example. It looks similar to Triton. So here are the differences between Triton and TileLang. Honestly, I don't understand differences too much. I feel like both are good to learn. But Triton seems to be more popular, I guess. So I'll stick to Triton until I see clear reason to learn TileLang. I'm sticking to Triton for now. TileLang is also very new, April 2025, so maybe there are bugs, or time will tell if we should use TileLang instead. Maybe it is better, maybe it does achieve a bit more performance on some things.